Is Lucy supposed to be here?
Yeah, I believe Lucy will be here. I think Emerson and Everly are the only ones that I expect to be, the only ones that I expect to be out today, so.
For some reason, like those things in that like pencil shaving thing or whatever kind of look like meat.
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 Hold up. These things? In here? Oh, I see. It's the wood, right? It's the little wood shavings.
Yeah.
Actually, that's getting pretty full, isn't it? I'm gonna have to empty that one now that you pointed it out to me. It's looking a little crazy.
I didn't do all the midterm, but
Oh, no, you don't have to. You've got a long time.
yeah.
It's just practice. I thought when your mom told me, she got a little freaked out because she thought, oh no, is this next week? No, you got lots of time. I give it to you plenty early so that you have lots of time to practice. And you don't have to feel like you haven't had time to study or whatever. I want to make sure you've got lots of study time.
It's not due for a while.
Mm-mm.
And what are all these?
Oh, those are for the other class is going to be doing some oh, it's okay. They're just going to be doing some calculations today, and they might want that. Got to animate that. And this means that if I don't, it'll fall asleep.
Can, this is a weird question, but can Alexa set off a nuclear bomb?
Not mine. Maybe somebody else has theirs programmed accordingly. But mine will not do that, thank goodness. I don't want it to. I hope that nobody's is programmed to do that. Let me see, where do I want here? No, that's like a...
Yeah. Plus, just the way I cough, like I have this old cough that I've been using for a while.
An old cough you've been using for a while? Yeah. It's good now. Come on, why am I clicking all the wrong buttons?
Is Eunice supposed to be coming?
Yes, it'll be you and Eunice and Lucy today.
Okay.
So what'd you do this weekend? Anything fun?
Well, I'm actually I'm part of the Forsyth County Democrat.
Yeah. You go do something?
Yeah, we went to a rally and I got free merchandise and free food.
Oh, good. You had fun, huh? That's great.
Student not tinkered yet.
Not yet. I checked. I keep checking. I keep hoping.
Tinker Day comes on a Tuesday.
Well, here's the thing. Next week is the last Tuesday of the month, so it's going to be our donut day regardless of whether or not it's actually Tinker Day because it's the last Tuesday. So we will be doing our donuts regardless. So there will be donuts next week, even if it's not full on Tinker Day. Because it's coming soon.
Yeah. Me and Luke intentionally remember that week when we were doing like periodic table battleship?
Uh-huh.
Well, after we were finished, we just decided to like take a little break and draw for the rest of the class.
Uh-huh.
And so when we talk a lot, we have a lot more common than I thought we did.
You and Lucy?
Yeah,
Cool. What'd y'all draw?
I don't know what she was drawing, but I was drawing like this kind of drawing where like first you would start with a square or part of a square. You would draw a semicircle.
Okay,
That then you like make all these little lines and all that like
okay.
across there like that. But it takes me a few hours to do this usually,
Mm-hmm.
or on a regular size, and then like you put lines in the middle of them and like make like little meteor shapes, and once you're done, then you color it in, and there you go. You have a square brave drawing.
Miss Danny,
That's pretty cool. Yes, sir.
why didn't you ask us about the oil spills last week? This one?
Last week?
Yep.
Oh, because we were talking about, how there are polar and non-polar
Oh.
bonds.
So we didn't do the oil spills?
We just talked about it. Did you need answer to something? Or did I
No,
not?
I already posted answers, but
Oh,
I had to.
you got it.
Like with lesson 6, I wrote all of this stuff. So
Oh, yeah.
so like dang, fudge, be saying,
You made them into words.
saying,
That works.
So are we the
Yeah,
only students?
No, Lucy's coming.
What about them?
Yeah, the twins aren't here, but Lucy.
Vodka. And then this one thing was gun, and so I just put a gun there, and then I replaced the Y and M with D and N, so it was D.
Okay, you're busy. There you go. Like it. I like it. You're a busy girl. You
Yeah.
know what you're doing over there.
There's this teacher did Splatoon that I want to get to, and I've got to get it before the end of the season. So I've got that, and then I also got like
What
a whole
season?
bunch of bracelets. I've
Just
got
like the
to-
fall, you mean? Like the end of the fall? Is that what you mean by end of season or is there?
Like in Splatoon 3's drift.
Oh, in the game season. Okay, in the game season. Gotcha. All right. Cool. It's all right. That's normal human behavior. We all cough. We all get things. It's a good thing that we cough, actually. It's good. It's your body saying, I don't like whatever this is. And it could be anything from a bit of dust to a virus to a bacteria. It could be pollen. Yep, my body does it with pollen. My body hates the pollen.
Eats pollen.
Yeah. I get so weird, like if I walk barefoot outside, when the pollen's landing everywhere and it gets on my feet, because it's on the grass, then my feet start to itch really bad.
Itch.
Yep. Yucky. I have an overactive immune system though, so I have all kinds of like weird things that really can't be accounted for. I'm not normal, y'all, so as long as you know I'm not normal, we're good. I'm most definitely not normal.
Hey,
So won't Google say like when's Tinker Day?
No, because Google doesn't know. The only person that knows is our president. Only
Was
person
the
who knows.
president made up Tinker Day?
The president of Hollins. Yeah, Mary Dana Hinton is the only one who knows when she gets to decide. She's the only one who gets to decide. So she's the only one who knows. But it's gonna be
Your
sometime in the
women's
next couple
college
days.
president,
Mhm.
she's the one who made up Tinker
Well,
Day.
she didn't make it up, but she gets to decide.
yeah, if she made it up, she
She didn't make it up. There are pictures of it here that go way back. This is a historical perspective, because it's a,
Tinker Day.
well, of my college, because it's an old school. But if
Were you in the pictures?
none of these, this was printed before I even went there, let alone before I graduated. And if you look up Tinker Day here, there's pages and pages, 49, 130, 137. There's pictures of it through various years, so like page 49. No, there's this one. That's Tinker Day. That's Tinker Day in 1898.
1898.
1898. 130.
I think you can erase pencil markings on your skin by
1949.
There's a mention of it over here, another picture. And let's see, 137. These are skits they were doing on Tinker Day that they did back in the theater for some reason, I don't know why. 38 and 39. These are pictures. Oops. These are all Tinker Day.
When was this?
These are, let's see. What date on that?
1940?
1970. On that one, 39. I don't know which one that, I think it's
These are
this one.
old.
Yeah. And then there's another one on 174. There's another Tinker Day picture.
What's this book about?
It's just a Holland's book. There's Tinker Day right here. 1950. They're all running up the mountain. And then there's one more on 250.
Yeah, I bet when you learn about Tinker Day, you're like, what the heck is that?
There again.
Again.
And this is Tinker Mountain, right?
Oh.
That's the mountain.
Yeah,
Yep.
So your
There's all kinds
college,
of cool
so your
pictures.
college invented Tinker?
Yeah, it's only in Holland. That's the only place it's a thing. But there are some really cool historical pictures in here.
Can you ask your president to choose Tinker Day on a Tuesday?
I can't ask, she wouldn't listen to me anyway. She's got a lot going on. She gets to pick and choose.
Only the president gets to choose it?
She's the one. It's a privilege of being president
Where's Holland's University?
in Roanoke, Virginia.
shouldn't Joe Biden be choosing
No,
it since he's technically the president?
he's not Holland's president though.
I know.
There she is. Good morning. How are you? Excellent. Well, the twins aren't coming today, so this is us.
Hey, are any of you guys left-handed? Because me and my dad are.
Are you?
Right-handed. Same.
I have a cousin that's left-handed, but that's it.
I have
I also have a cousin
who
who's left-handed.
is both handed.
Mm.
Happy Halloween.
Ambidextrous. I had an uncle who was ambidextrous.
Like-
He played guitar with one hand and he wrote with another hand and caught a ball with the other. It was weird. Yeah, it was very strange. He did certain things with certain hands, he didn't switch back and forth.
Sometimes kick the ball with my left leg and stuff.
What were you gonna say?
Did you turn your Dotson into a plushie or a skeleton?
Yeah, that's cute, isn't it? I saw a skeleton out front.
Yeah.
No, but so my cousin, not the one who's left-handed, my cousin used to have this substitute teacher at her elementary school. And I so wish they would send this lady to my elementary school because she was ambidextrous, but she would do this thing, guys. This is how she'd start class. She'd say to the kids, "All right, kids, my name is," and she'd turn onto the blackboard and she wrote her name in mirror image. So with her right hand, she was writing normally. With her left hand, she was writing it backwards that way in cursive, mirror image. And then she'd say, "Hiya," and turn around into a split in front of the whole class. That's how she started class. My cousin was like, she was the best substitute teacher ever. She always wanted her
In a public school?
in a public school. Yeah, I was like, I had never had that teacher. I would have remembered that. She told me about it. She's like, I've never seen. She wrote it. It was like mirror image. She wrote her name, and it was some long last name too. And it just kept going. Like that's really fun. Okay, are we ready to start our Q2 officially? So if I did some grading yesterday morning, but if you turned your unit 4 test in later than yesterday morning, I haven't seen it yet, but I will get to them. So I think the 2 of you were the only ones that I had done. And then y'all will get your progress report sometime in the next couple of days with your quarterly average on it. Yes?
Progress report.
You what?
I think I already got my.
No, I didn't send it yet. I've been working on it. Yours is done, but I haven't sent it yet. It's not in the right format to send, and I send them all like at this. I sit down and send them all sometimes.
Score.
I'm not telling you. All right, let's have a look. So we are now in Unit 5, and we're going to start learning about some types of reactions today. And we've gone over some of these a little bit before, so they shouldn't be too foreign to you. But we're also going to talk about, again, remind ourselves the difference between physical and chemical changes. So what is a change of state or form without a change in chemical composition, Annabelle? That is a physical change. You're right. And when you have one or more substances that are altered into one or more different substances, what's that, Eunice? That is your chemical change. Okay. So physical changes don't change the substance, right? They can change the phase or the state, but not
Like
the
it
substance.
Water, but phase water.
Right, it's still chemically water, right? Right. But when you change the substance itself, then you have a chemical
Like when you
change.
turn, wood into ash, it's chemical.
Yes, yes. All right, so what are some signs of chemical changes? So we're going to get to guess what some of these images are showing, okay? They're going to be demonstrating some signs of chemical changes. All right, what do you think this photo represents for a chemical change, an indication? What do you think, Eunice?
A color change.
A color change. If a color changes, that is a good example or good indicator that a chemical change has taken place. Can you think of an example of this in real life? What do you think?
Like when when an algae forms into an apple.
Like when an apple does what now?
When an apple gets rusted or
Like
something.
it rots, it changes
rots,
color?
rots.
Yeah.
And like or when an avocado rots.
Uh-huh.
Or when like or when like sorry.
You're fine.
Or when like
So-
time like like something thing might like color change if it's dipped in cold water like that.
Mm-hmm. That could sometimes that could be. Okay, so let me ask you this, Lucy. How do you know that a berry on a vine is ready to eat? How can you tell when it's good to pick it? Have you ever had blackberries or strawberries or?
I've had blackberries that are same.
Oh, you don't like it? But how do you know when they're okay to eat? What should they look like?
Black.
Yeah, what color do they start out?
Red.
Red.
And before that?
Green.
Green. Okay, and those are all chemical changes that are occurring. And that's how you know when that fruit is ripe, right? So fruit ripening is an example too. All right, so a color change. All right, now, what do you think this is representing? What do we think? All right, Eunice, what do you think?
Production of an odor.
Production of an odor.
Issues.
Stinky. Anybody have ever been like, oh my God, my shoes smell really bad?
Yeah.
Sometimes when I exercise, my feet smell.
Yeah. Okay, so you guys have seen in my weekly emails, I've been like, we have some stinky people in class and we need to fix the stinkiness, right? What's causing the stinkiness? Why do we human beings smell? What
Because
causes
we're
it?
not using deodorant, we're not showering.
Right, but what causes the smell? What do you think?
Sweat.
Part of it. So you actually have little bacteria that live on your body and they're good for you. They're normal. We call them your body's flora. You have them that live in your gut, in your intestines. You have them on your skin, and they're essential for you. If you didn't have them, you'd probably be sick all the time because it's a healthy relationship. You're supposed to have a certain amount of we call them good bacteria, but they're beneficial bacteria is really the better way to say it. But some of those bacteria that live on your body, they like to eat the stuff like dead skin and sweat. They enjoy eating it. And then what do after they eat it? What do? You know?
You get sick.
No. They don't quite poop it, but it's kind of like they burp and fart. They produce gas. So these little bacteria make this gas and it stinks. And that's why we stink if we don't, keep a good bath. And also that's what deodorant stuff does is it either covers the stink or it prevents the stink. Like the stuff I suggest in the email, that Lumi and Mando, what it does is it changes the pH or the acidity level of your skin and makes it so those bacteria can't do that. So then you don't stink. Yeah.
Are the white blood cells good bacteria?
No, those are blood cells. You make those. They're not bacteria. Those are part of your body. But those are part of your immune system. They actually are the ones that some of them actually fight bacteria, depending on their purpose. There's all kinds of different ones. But yeah. Spinning. It's all good.
That was the thing I love about on my head.
It's all good. So yes, production of an odor. This is also, how do you know when you ever have I have a bowl of fruit that I move off the counter every week. And yesterday I had it sitting next to me and I was getting ready to move it and I was like, one of those limes has gone bad. You ever smell like when fruit starts to rot, you can smell it too. So not only does it change color, but it stinks. All right. What do you think this one is? Annabelle?
Chemical change.
It's a chemical change. What type are we seeing here?
We're
You know what it is?
seeing like morphing.
What do you think?
Looks like a precipitate.
It's a precipitate. Okay, so a precipitate is when you mix two liquids together, two solutions, and there's a chemical reaction that takes place and a solid forms. And they call that solid will appear right there. You can see it's like milky, right? It's just when the chemical, it depends on what's going on, but in a chemical reaction, you may have, yeah, you may have certain elements that are going to recombine, and they don't recombine in solution anymore. They're now insoluble. So they recombine and they form a solid. And here's a great chemistry term. We have some fun terms in chemistry. This is one of my favorites. When a precipitate forms like this, they call it crashing out of solution. Isn't that fabulous? It crashes out of solution. Yeah. And you will be forming a precipitate in a lab, and it'll be fun. You'll be able to see it. You'll be like, oh, look at that. Because they tend to look milky because the water, like the light can't pass through the solid particles that have formed. So that's what you see. All right. Butterfly milk? No, what's that?
It's milk from butterflies.
Well, what does that mean? Like what?
People milk butterflies. Butterflies have milk in certain kinds.
Some kind. So probably not the same kind of milk that mammals have, but probably something.
Like used to maybe make silk.
Oh, maybe yes, as when they are, yes, in their larval form. Do you know how to tell the difference between a butterfly and a moth? Do you know?
I think butterflies have two wings and moths have one.
No. So some people will say
Other way around.
you see moths at night and butterflies during the day, but that's not necessarily true. The way to tell actually is if you look at their antenna. So butterflies have a long, thin antenna with a little ball on the end, like a little knob on the end. But a moth's antenna looks like a comb or a little brush. It's not straight. It's got all these little fingers on it. Order Lepidoptera have fuzzy little antennas.
Fly like this and moths fly like a falling.
Oh, okay. There's
One
another one.
time I saw this.
Oh, like a Luna moth? The big green ones? They're beautiful. They're beautiful. I love them. And they only live
They
like
had a hole in its
really.
wing.
So I think that's a temperature change.
That was my question. There it is. That is a change in temperature. All right. What's an example of that in real life? When might you see a change in temperature that indicates a chemical reaction? Annabelle, what do you think?
Boiling water.
That's going to be physical.
Oh.
So when would it be a chemical change? You got an
We
example?
add color to it.
We add color?
No.
No? Anybody ever use a ice pack or a hand warmer, the kind that you pop and break, the ice packs that you pop and break and shake it?
No.
Oh, yeah. They're little plastic ice packs and they have like a little bubble inside, another container inside that keeps the two chemicals separate. And when you pop it, you break the internal bubble and it will cause the two things to combine and it gets cold. And then there are the hand warmers that you bend and shake like that, and then they will warm your hands up too because it's a chemical reaction. So a change in temperature. And we will have some reactions this year where you will see a change in temperature. All right, now what would this be? Anybody know? You want to guess, Lucy? What's that, do you think? What does that look like to you?
Water and salt.
It's water. It's not salt. Those are bubbles. So what do you think it might be showing you? What would bubbles in water show? Or in liquid? What do you think, Eunice?
Gas.
Yeah, evolution of a gas. So sometimes a gas is formed in a chemical reaction, right? And then it becomes more obvious because you can see the bubbles. Sometimes you can hear the bubbles.
I have an example, like you see the bubbles in a bread, that's an evolution of the gas.
Yes, that is. That is like when we talked about how the little bacteria that live on your body can burp and fart out gas. So can yeast, which are fungus. And we use yeast when we make bread. It's a fungus that we use. And that fungus produces gas when it eats the sugar in the bread. And then that's how you get the bubbles. Yep. Also, the old standby baking soda and vinegar. You get bubbles, right? Right. All right, so let's talk about reactants now. And there are others, by the way. There's production of light, there's production of sound. Like you can see production of light, like the close. Okay, there you go. You can hold it from now on, so you don't have to worry about it doing that again. There you go. Production of light, production of sound, like sometimes there's a chemical reaction that occurs within fireworks, and then you can hear the sound, right? And then there's also the emission of electricity. Sometimes that's an example too. So let's talk about reactants. All right, now what are reactants? So anybody want to define a reactant for me? You want to do it, Eunice? What's a reactant?
The reactant is what? Reactants are two chemical like. Can I give an example of one?
Yeah, you can do that.
Like oxygen and air are reactants. They form a rot.
Kind of. Well, so let's see. So a reactant is a substance that takes part in and undergoes the change in a chemical reaction. So these are the things you're putting into the reaction. And where would you find them when you write out the chemical reaction? Are they going to be on the left or the right of the arrow that we put when we write down a chemical reaction? Do you know? On the left or the right? So they're going to be on the left. And so it'll look like this: reactants, and then an arrow, and then products. Do we know what the arrow means? What's it mean?
It means you're going right.
Right. So it means the word you would use to replace that arrow is yields. These reactants yield these products. Not yield like there's a sign that means slow down and look, don't totally stop. Yield as in produce or create. So you put these reactants in and they create these products. They yield these products. Okay.
So when oxygen and when the apple and air are the reactants, and then the product is a rod.
Oh, the rotting is. So yeah. So it's actually specific chemicals that you're seeing. And we just call it rotting, but there's a lot of very specific things going on in there. But yeah, a reactant would be if you put baking soda. Anybody know what baking soda's chemical name is? Sodium bicarbonate with vinegar, which is acetic acid. You put those two things in, they're going to produce a gas, water, and a salt.
Gas, water, and a salt.
Yep, a gas, a water, and a salt. And if you know that you have, well, you'd have to know the chemical formula for acetic acid to see it, but you could figure out what salt is produced in that case. Okay, so how about then, what are the products? Anybody want to try and define products? We just defined reactants. What do you get, Annabelle?
The product is like a result of something, and
Is like what of something? I couldn't hear you.
it's like a result of
A result, okay.
two elements or something.
Yeah, yeah. So it's the substance that is formed in the chemical reaction. So when we're taking our example of baking soda and vinegar, its products are going to be water, a gas, and a salt, because anytime you mix an acid and a base, they're going to produce water, a gas, and a salt. That's what happens.
Can you get another example besides vinegar and baking soda?
We're going to have a lot of them. Don't worry, we're getting there. You're going to see so many in the next couple of weeks and months. You're going to be like overwhelmed with chemical reactions. You'll see them all, tons of these. Okay. You're going to learn how to balance them too. It's kind of fun. So if the reactants are on the left and the products are on the right. So again, it looks like that. Reactants yield products, right? Right. Okay. So then we have different kinds of reactions as far as what happens to the energy. We have endothermic and exothermic reactions. What kind of reaction absorbs the energy in the form of heat? And it's the kind of reaction in which chemical bonds are broken and it tends to feel cold. Do you know, Eunice?
Endothermic.
Okay. So in this case, yes, your endothermic reactions feel cold. So those ice packs that you use when you have an injury and you pop it and you break it and you shake it up, they feel cold. So that is because bonds are being broken. And in order to break those bonds, you have to absorb energy. And when you absorb energy, you're going to feel colder than your surroundings. But what's the kind of reaction where bonds are formed and you're releasing energy? What's that?
Exothermic.
Exothermic. Very good. You're going to release those exothermic reactions are going to release energy in the form of heat. Bonds are being formed, and because energy is being released, it feels warm, right? If you release energy from something, it's going to feel warm. So what kind of reaction do you think goes on in your body metabolically? What do you think when your body is like breaking down sugar and using it for energy? Which one of these reactions do you think it is? What do you think?
Breaking down sugar. So
This would be cellular respiration. This is the process that keeps you alive. What do you think? Is it going to be?
so
Yeah, because how do you feel?
hot
You're warm, right? That's why you're warm. You ever wonder why you're warm?
because of that.
Why are you warm? Why are you not the same temperature as the floor and the couch? Why are you 98.6 degrees Fahrenheit roughly? That's why. Because you are forming bonds, and it's a whole process, cellular respiration, aerobic cellular respiration, but you're feeling warm. All right, so now we're gonna do a little quiz, right? We're gonna hope we don't get, oh. Come on. Oh no. Okay, I can't make these stop, so we're just gonna have to endure it for a minute. Yes, we know. They'll be done soon, I hope, because I'm real tired of them. Yeah, we know.
Take notes as you watch this video and take the short quiz at the end. Every day, we observe a myriad of changes around us. A car can get crushed into a compact cube of metal at a junkyard. A fire can burn logs in a fireplace, turning them into ash and smoke. Bread bakes to a crispy golden brown loaf. And metal rusts when exposed to moisture and air. Each transformation, whether big or small, is a testament to the ever-changing nature of matter around us. In science, we dissect these transformations and categorize them into two primary types: physical and chemical changes. In a physical change, the form or state of matter changes, but the molecular structure remains the same. No new matter is made. For instance, consider the process of ice melting. As the temperature rises, the ice transforms from a solid state into liquid water. Even though the state and appearance change, the water molecules are still H2O, maintaining their original molecular structure. This transformation illustrates a physical change, where the state alters without changing the substance itself. Let's take a look at some examples of physical changes in action. Consider a sheet of paper. With a pair of scissors, the paper is cut into smaller pieces. The shape and size of the paper change, but chemically, it is still paper. Each piece retains the same properties as the original sheet. Another example of a physical change. Now think about a piece of modeling clay. In your hands, it can be molded, stretched, and shaped into various forms: a ball, a cube, or even a miniature animal. Though the shape transforms, the composition of the modeling clay remains consistent. The changes are physical, not chemical. Consider the act of making a salad. Crisp lettuce is torn, vegetables are sliced, and ingredients are mixed together in a bowl. The various components change in shape and texture as they are prepared and combined, but their chemical composition remains the same. The lettuce is still lettuce. The tomato remains a tomato. The salad, brimming with an assortment of colors and textures, exemplifies a physical change.
That makes me want salad.
Visualize a glass falling
Pretty
to the
picture.
floor and smashing into pieces. The integrity of the glass is compromised. It shatters. However, each fragment, sharp and irregular, is still glass. The chemical composition hasn't altered. Thus, we are once again witnessing a physical change. Chemical changes involve a transformation at the molecular level, where the original substance turns into a different substance with new properties. It is characterized by the formation of new chemical substances and often involves energy changes, evident through the release or absorption of heat, light, or sound. Various indicators like change in color, production of gas, or the formation of precipitate can denote a chemical change. When iron is exposed to oxygen and moisture, it undergoes a chemical change resulting in the formation of a new substance, rust, iron oxide. This is evident by the change in color from metallic gray to brownish red, and the alteration in the material's properties like strength and appearance. The chemical composition of iron changes, proving that it's not just a physical alteration, but a chemical change. In a fireplace, wood burns and transforms into ash, heat, and gases. This is accompanied by the release of light and heat, indicating a chemical change. The original wooden logs, primarily composed of cellulose and other organic compounds, are converted into new substances like carbon dioxide, water vapor, and ash. The visible flames and the change in material composition underscore this transformation as a chemical change. The solar.
No, a mid-video commercial. Could it get any worse?
Don't say that, don't, we'll get worse.
Truth.
Ingredients like flour, eggs, and sugar are baked, they transform into a cake. It's not just a state change. New compounds are formed during the baking process, changing the taste, texture, and color. The cake's aroma and the solidified fluffy texture are evidence of a chemical change where new substances with distinct properties are created. Plants convert carbon dioxide and water into glucose and oxygen using sunlight. This transformation is marked by the emergence of new substances, glucose and oxygen, which were not originally present. The absorption of light energy and the creation of food and oxygen signify a chemical change. When baking soda and vinegar are mixed, there is an immediate fizzing and bubbling reaction. This is due to the formation of carbon dioxide gas, a new substance. The chemical reaction occurs as acetic acid in the vinegar reacts with the bicarbonate in the baking soda to form carbonic acid, which quickly decomposes into water and carbon dioxide gas. The evolution of gas, change in temperature, and the formation of new substances like carbon dioxide, water, and a type of salt are clear indicators of a chemical change. Do you think you can identify changes to matter as either physical changes or chemical changes?
Yes.
Let's put your knowledge to the
Okay,
test.
here we go. It's a quiz. Let's see. How do we do? Okay, photosynthesis, chemical or physical? What do we say? Chemical or physical? Who says chemical? It's chemical. Very good. Right, what's the next one gonna be? They're giving you time to read that. Photosynthesis, carbon dioxide and water. Okay, boiling water, chemical or physical? Who says physical? Me too. Anybody say chemical? Nobody said chemical. No. And that's because water is heated to its boiling point, transforms from a liquid state to steam or vapor. May change the molecular composition, make the physical change because the molecular composition of water remains the same, only its state changes, right? All right, how about this next one? Digestion of food, physical or chemical? Who says chemical? Who says physical? I say both, actually. There is a physical component. The mastication, the chewing is a physical component, but the actual digestion is chemical. So inside your body, food we eat is broken down by enzymes. Those are catalysts. We'll talk about that. Into simpler substances. Yep, into waste. Burning paper, physical or chemical? Who says physical? Who says chemical? Go. Burning paper is going to be chemical because you see a color change, you see production of heat, you see production of light. You know it's going to be a chemical change. New substances are formed. Ashes. Ashes weren't there before. They're new. And gas. Yep. Okay, how about crushing a can? Who says physical? Who says chemical? Good. Still a can, right? Can is a can, even if it's squash. Very good. Material remains the same. Right, what's the next one? It's a little slow. Come on. There we go. Dissolving sugar in water. Who says physical? Who says chemical? Oh, we're not sure. It's physical because it's still sugar. If you evaporated the water, would you have sugar?
Yeah.
Yeah, you'd still have the sugar would remain and the water would evaporate off. So sugar molecules are still sugar molecules and the water molecules are still water molecules. They're just in solution with one another. Okay, cooking an egg, physical or chemical? Who says physical? Who says chemical? The breaks in the egg is going to be physical, but then once you cook it, those proteins denature. It goes from being that slimy thing to being much more firm, that cooked egg. So that's that's how you know it's a physical change because you've had a difference in color, a difference in substance. Okay, melting wax, physical or chemical? Who says physical? Who says chemical? It's physical to melt the wax, but the flame, if you're using a flame, that flame would be chemical, whatever it's burning. But the wax itself is still wax. As soon as it cools down, it just becomes wax again, right? Like solid wax instead of liquid wax.
Burn the crayon and then it's still.
Yeah, it's still just a crayon, it's just in a different state. Very good. How'd you do? How did you go? Because we're Australian here, so we say how did you go instead of how did you do?
You're Australian?
No, that was stop. Oh my gosh. I want it to end. I want it to end so bad. Me neither. Can't wait. Okay. Whoops, there's your first one. Okay, so any change that alters a substance without changing it into another substance is, everybody together, a physical change. What is something that has mass and takes up space? You don't have to yell it, but yes, matter. Okay. A reaction that releases energy in the form of heat is called what kind of reaction? Everybody together? Exothermic is right. Check your answers, right? Make sure you got these. What is a reaction? What kind of reaction is it when energy is absorbed? Endothermic. A chemical change is also referred to as a what? Chemical reaction, right? All right, and then what is a solid formed when liquid reactants from liquid? I cannot read. Yes, a precipitate. Very good. All right. Now we've got to decide here observable changes and types of change. What things do you observe when a cake is baking? Let me see. Let me ask Lucy. Lucy, what kinds of things do you observe when a cake is baking?
It rises.
It rises. There's one. Anything else? What do you think?
Color change.
Color change. Yeah, especially if it's a light colored cake like a vanilla cake. You can see that golden brown. And you said rising. Rising is because there's gas being produced. So we have evolution of a gas. We have a change in color. What else do you notice?
Change in temperature.
But that's because the oven's heating it up. Remember that observation is all of your senses. If you're up in your bedroom, how do you know your mom's baking a cake downstairs?
The smell.
Ah, yes, production of an odor. There you go. So yeah, you could see a change in color, change in texture, smell, taste change, batter rises, small holes appear. So what type of change is this? Physical or chemical? Chemical. You want holes. You don't want tunnels. Tunnels in a cake or not. That's a poorly baked cake. It means it's overmixed. If you bake your cake and it has these vertical tunnels in it, that means it's overmixed, but whatever. How about burning a log? Okay, what are some things we observe with burning a log? What do you observe?
It becomes harder and will burn and breaks down into smaller parts.
It's changing into a different substance, right? Because you could do that with an axe or a wood grinder or whatever, a wood chipper, but it's changing into ash. What else?
Color change.
Color
and
change.
Production of the gas.
Production of gas. What gas comes when you're burning a log?
Carbon dioxide.
And yeah, and carbon monoxide comes out, you get that
I
smoke.
burn a lot of wood.
Oh, yeah, so you'll notice changing color, log turns black, produces smoke, heat, and light. Grayish black ash appears, there's a noticeable smell. So is this chemical or physical?
Oh.
It is a chemical change. All right, freezing water, what do we notice? What do you notice?
Change of state.
Change of state, what's it look like? How do you know it's changed state, Annabelle?
When it's become a solid, but
When it's suddenly a solid. What else do you notice about water when it freezes? Anything else?
It remains, no, it remains a cube, that's what I was about to say.
It can be a cube, it takes the shape of
Yeah.
whatever. Did I mention this to you guys? I know I talked about it with the other guys. I'm not sure if I mentioned it with you. But if there's ice in my glass right now. Okay, in my tumbler. Okay, I have water and ice in here. The water's in here and there's ice in here. Within here, where would you find the ice? At the bottom, at the top, in the middle?
Bottom.
At the bottom? Is ice
Because
go to
it's
the
the
bottom?
heaviest.
Hmm?
Because it's the heaviest.
So if you put ice in water, does it go to the bottom? Think about it.
No, the top.
Where does it go?
Top.
It goes to the top. Why does ice float? Oh, good question. Now, here's a thought. When most things are chilled, they become more dense, right? Because there's less motion within the particles and things tend to condense and they become more dense. When things are heated, they tend to expand, right? So what happens to water? Water's different. And it's not because of the H2O, it's because of what H2O does next to another H2O. There are hydrogen bonds that bond water to water, okay? And those bonds cause water when it freezes to crystallize, to form that lattice, that crystal kind of a look where they stretch out. Most substances do not do that. Water is different in that way. And it's important that water's different that way because if ice, and it makes it less dense basically when they spread out like that. If ice didn't float, think about what would happen like to a pond. What would happen to the fish that live in the pond if the ice started at the bottom or froze the whole way
It has to be
through?
destroyed.
Right, we need ice to float. That is essential for life on Earth. The fact that ice floats and doesn't sink to the bottom. So it's one of those little things, like water is essential to life, but not just water, but the actual characteristics of water are very important, and that would be why. So yes, you see liquid water is now solid ice. You have a change in texture, sometimes color. You can see sometimes it refracts the light differently and ice looks a little bluer. You ever seen an iceberg?
Yeah.
Icebergs look very blue, right? It's interesting. And volume, and then there's a density change. It will float on it. Water that is frozen will float on water that is liquid. Water will float on water, basically. And then how about, is it physical or chemical?
Oh.
It is going to be physical. Okay, now this is quick, but you're going to hear about moles today in lab. And I want to make sure you have some understanding of what it is before we get there. Oh, God. I'm so tired of them. I wish they would go away and I can't make them. I even play these before class so that hopefully it doesn't happen and it still happens.
So Avogadro's number is an incomprehensibly large number. It has to be. It equals the number of particles in a mole of something. And in 2019, that was defined as exactly 6.022140.
Actually, you know what? No, it's okay. We can play it. We probably won't finish the whole video before.
And as a
They cut
chemistry
it,
teacher,
but
I'm
just so you know.
contractual obligation to love this number. I even got married on October 23rd, which is International Mole Day. I'm not kidding. I'm all in on Avogadro.
International Mole Day.
Now, chemistry.
Tomorrow.
We're all trying to use Avogadro's number and fusion conversions to show how big it is. But in the end, I don't think they're very helpful. There are lots of big numbers we could use in fusion conversions, and the story of Avogadro's number is so much more than the number itself. So if you really want to impress somebody with Avogadro's number, don't do conversions. Tell them stuff like this. Tell them that the scientific acceptance of atoms hinge on finding Avogadro's number. You see, starting back in ancient Greece, there were two camps when it came to the nature of matter. One camp, led by Aristotle, thought that matter was continuous, and you could continue to subdivide matter smaller and smaller onto infinity. The other camp, led by Democritus and friends, argued that you could only chop matter so far until it became uncuttable, atomos, as the Greeks called it. So for the next 2 millennia, the debate raged, but the atomists slowly started to pull ahead. Despite running up the score, Team Atom proved in the game. The problem was that no one could actually find an atom. What if atoms were so small that they were beyond experimental reach? To really establish atomic theory, scientists needed to find the absolute weight of atoms. And to do that, they needed Avogadro's number. Editorial note here, I'm going to stop using the term Avogadro's number for a while because this story starts at the beginning of the 19th century. And that honorary title would not be bestowed for another 100 years. So with that in mind, let's just call it secret number N for now. So if your friend isn't impressed yet, tell them that Avogadro's number was a powerful idea even before it was a number. In 1808, Dalton theorized that atoms of different elements had different and distinct relative weights. Dalton knew he couldn't find the actual absolute mass of atoms. They were much too small, but he had a hunch he could determine their relative masses, the mass of atoms compared to each other. So take, for instance, hydrogen and oxygen. Dalton thought that 1 gram of hydrogen would react with 7 grams of oxygen. So if those large laboratory piles of atoms had equivalent number of atoms, then the laboratory mass ratio should scale all the way down to the atomic level. So think about that. The relative mass of the atoms would be hydrogen 1 and oxygen 7. Take a look at the periodic table. Hydrogen's atomic mass is still right around 1. Dalton made a lot of mistakes for sure. If you look at the periodic table, the corrected relative masses are actually 1 to 16, not 1 to 7. But the big idea remains. We have an atomic mass in Dalton's, and we have a laboratory mass in grams. It's the same number. It's the same reason why gold can be 19.3 grams per milliliter and 19.3 kilograms per liter. It's because the top and the bottom scale up by the same number, 1,000, so the ratio doesn't change. The number that connected those two realms of existence wasn't 1,000. It was astronomically larger. It was secret number N. But since it wasn't a direct part of the relationship, since it canceled out, scientists were doing just fine without knowing what secret number N really was. So if ratios aren't really your friend's thing, tell them that Avogadro never actually came up with Avogadro's number.
His name
In
sounds like
1811, he was just an Italian physics professor with a different take on the Gay-Lussac discoveries.
Avogadro.
Gay-Lussac had noticed that when gases react together, they tend to do so in volumes which bear simple whole number ratios. Avogadro correctly took this to believe that equal volumes of any two gases under equal conditions contained equal numbers of molecules. Avogadro had a theory, never had a number. The actual number of molecules in those equal volumes was unknowable and frankly irrelevant as long as they were identical, as long as there was the same number of molecules in each. Now, unfortunately, Avogadro's contributions were largely ignored during his lifetime for a variety of reasons. He might have been completely forgotten, save the efforts of a fellow Italian named Stanislao Canizario. 4 years after Avogadro's death, Canizario would reintroduce the world to Avogadro's ideas in the waning hours of the world's first international conference of chemists, the extraordinary Karlsruhe Congress of 1860. Canizario used Avogadro's idea to lay out a convincing argument for what would become the basis of our current established relative atomic weights. People were impressed. One of those new devotees was none other than Dmitry Mendeleev, who, inspired by the strength of Canizario's advocacy of Avogadro's idea, would publish the first true periodic table within a decade. One of our biggest failures when we talk about secret number N is to leave out all the unique and clever techniques used throughout history to try to determine its value. There have been lots of them over the centuries, at least 6.02 times 10 to the 25. But this video isn't going to get into all of those attempts. There were lots of famous names along the way: Faraday, Millikan, Planck, Einstein. That's right, Einstein. It was the 20th century and we still hadn't definitively verified the existence of atoms. Think about it. Einstein had to take a break from his theories of relativity to help push this across the finish line. Finally, in 1909, Jean-Baptiste Perrin experimentally validated Einstein's theories. It involved an ultramicroscope and some tiny colloidal spheres, but in the end, he would finally have observable phenomenon that validated the existence of atoms. Perrin had 3 different experimental techniques that each independently validated very similar values for secret number n. After that, it became intellectually indefensible to further deny the existence of atoms, and this would earn him a Nobel Prize in Physics in 1926. Perrin, in a truly class act, recommended that the value of no longer secret number n be henceforth known as Avogadro's number, in tribute to his critical early contributions. So when we bring up Avogadro's number, discuss how scientists were using it long before they ever found it. Mull over the fact that Avogadro's number was the secret conversion between the atomic and the macroscopic realms of existence, and that the fate of the atomic theory of matter rested on its discovery. Heck, name drop Einstein if you had to, but don't spend your time on the number.
So what is the number? Does anybody remember what the number?
0.002.
6.02 times 10 to the 23rd. Yes.
In the lab, when it
You lefties?
shows in here,
Mm-hmm.
you spelled it wrong.
Where?
Go back,
In the video?
no, go back,
To where?
that, right next to the moles and mule, here is spelled wrong.
Oh, you're right. You got a brownie point. Write it down so that I'm sure to fix it. Whoop. All right. Let's bring in your crew now. All right, Drew, will you tell your friends to come on down?
Do new lab teams?
Yes, there are. We'll be doing that today.